Today we're talking about functions, and yes, these are the same functions that you used in algebra and calculus, but today we're going to think about them in maybe a slightly different way. Now, if I asked you to think about the function f of x equals x squared, what comes to mind? Well, at least for me, it would be the graph of the function that looks like a parabola. This is a great way of thinking about it, but I want to go back to a common explanation of functions that someone might hear when they're first learning about them. Namely, functions are often described as some mysterious box that if you give it some input, it spits out some output. And this is how I want to be thinking about them, at least today. This rule that if I feed a 2 into a box that's representing our function f of x, or in this case f of x equals x squared, I feed in a 2, I want to get out a 4. I feed in a 3, I get out a 9, etc. So this is how I want to think about functions today, as a rule that if you plug in something, you get something out. Now a graph like this is a useful way of representing how a function works. It gives us a good sense of what the rule is for how inputs get converted into outputs, but it's easy to forget the origin of this function, and that it's really just the rule itself. We'll say that a function from one set to another set is a rule that to every element in our first set, we assign exactly one element from our second set. We'll typically write this as f goes from A to B, and this type of notation is especially important when we start changing what these sets are, what the different possible inputs and outputs are to our functions. A little bit more terminology, this A, this original set, we'll call the domain, while the B, the set that is the target set, is the codomain. And we'll be talking more about what happens when we change what these sets are. But for now, let's go back to our original example, this f of x equals x squared. Well, the way I've drawn this parabola, this is illustrating the fact that when we plugged in a certain value, we get out a certain value. In other words, we are plotting the domain along the x-axis. So I'm calling this r, so this is our notation for all real numbers, meaning that the types of things that we can plug into this function, at least when we're usually talking about it, are any number. Really any number you can think of, you can plug it in, square it, and see what you get out. Right? And then the numbers that we get out are also going to be numbers that come from the set of all real numbers. Now, you may be objecting, saying that, hey, we're not actually going to ever get out a negative number. Well, that's fine. The codomain doesn't necessarily have to include points in what we'll call the image, or the range of our function. So for this particular function, a graph or a plot of the function does a particularly good job of illustrating what's happening, largely because this function is continuous. So what I mean by that is if we plugged in a certain number, the answer that we get out, the result of the function, is similar to the answer that we would get out if we plugged in a number that was a little bit different. Courses such as real analysis delve into the nitty-gritty of properties like this when we're working with functions. What does it mean for something to be continuous or integrable, or properties like that, which is all well and good, but this is a discrete math class. This function, f of x equals x squared, at least if we define it to go from the real numbers to the real numbers, as we have here, as we typically can think about it, is not a discrete function. Right? This is a continuous function. We're concerned with all of the points in between them. For discrete math, we typically want our sets to have its entries be isolated. So if rather than working with the real numbers, we instead worked with the integers, then there are gaps between the numbers, and we don't have to worry about what's happening in between them. Probably the main reason that we want to formulate our definition of functions like we do here is that it allows us to generalize what types of functions we're even thinking about. Typically, if you've thought about functions so far, you're thinking about functions that go from the real numbers to the real numbers. And these things can look weird. You can have arctangent of x cubed or what have you. But we're going to be thinking about functions that go from different sets. So at their basic level, they're functions that work in different realms. So for example, let's think about a function that goes from a set A, just the numbers 1, 2, 3, and 4, to a totally different set, so something not even number related, the set of colors red, green, and blue. All right. So we're saying that a function is a rule, or it's a way of identifying all of the entries in A to an entry in B. So there's a few ways of representing this. One of probably the easiest, for at least if we have a relatively small set size, is to really just draw lines. Say that, all right, let's say 1 is red, let's say 2 is red, let's say 4 is also red, and 3 is blue. So this is a way of describing what the function does on each of the elements in the domain. F of 1 is red, F of 3 is blue. As one can imagine, this method of just drawing lines pointing from one set to the other set doesn't scale all that well. It's great for illustrating something like this, but it's not a great way for talking about a function in general. A more common technique for representing a function is to define the function to be a set of ordered pairs, where in each pair the first entry is an element in our first set, and the second entry is an element in the second set. So this ends up representing the same function that our lines did earlier on. 1 goes to red, 2 goes to red, 3 to blue, 4 to red. It's the same pairing, but just represented in a different way. All right. And then another technique for representing a function would be to graph it. So just like with our function f of x equals x squared that goes from the real numbers to the real numbers, we're going to put the inputs along the x-axis and the outputs along the y-axis in something like this. So because this is discrete, because these sets are discrete, the inputs happen at these certain points, so we wouldn't ever be drawing anything in the middle, but we can still represent what this function is by plotting points. So the function 1 goes to red, 2 goes to red, 3 goes to blue, and 4 goes to red. So this is the plot of the function that we've been describing. So again, the set A is our domain, and the set B is our codomain. So comparing this plot to our first example, f of x equals x squared, running from the domain of all real numbers to the range to the codomain of all real numbers, can be represented by a plot that looks like a parabola. All right. One more definition I want to mention is that the range is a subset of the codomain that consists of all of the points, all of the elements that is targeted, that is the result of the function f. So looking at our example 2, the codomain is the entire set B, which contains red, green, and blue. However, green is not the output corresponding to any of the possible inputs from our function f. Put another way, f doesn't ever target green. There's no inputs, there's no elements in the domain that has an arrow pointing at green. So as a result, we say that the range of the function f is the subset of the codomain that is just red and blue. So the range is just the set red-blue. Again, looking back at our first example, f of x equals x squared, going from the domain of the all real numbers to the codomain of all real numbers, has a range of only the positive real numbers and 0. So the negative numbers are not possible results of the function f of x equals x squared. There are two especially important properties of functions that we're going to talk about, the first of which is onto. So a function is onto if every element in the codomain, so every element in the target space, is hit by the function at some point. So every value b in the codomain, every element in this codomain, has a solution to this equation. B equals f of x for some number, or some element x, in our domain. So put another way, the function, if we think about it as pointing at things, the function points to every element in the codomain B. All right. We had just said that the range is the set of all of the elements in the codomain that are pointed to. So if all of the elements are pointed to, then the codomain and the range are the same thing. As an example, let's work with sets with relatively small numbers of elements, namely sets that have 3 or 4 things in them. So our first example is this function on the left. Well, a function goes from some domain to some codomain, so some set A to some set B, and we're not even going to bother giving these elements names, we're just going to label them with points. The function identifies to every point in A a point in B. So maybe let's do that, let's do that, and let's do that. So this function that I've drawn, that's represented by these purple arrows, is a function that is onto. And it's onto because all of the elements in B have an arrow pointing at them. Every element in B has the property that the function, when applied to some element in A, equals B for something in A. All right. Let's contrast this with another function. Let's say this function goes from A to B, so notice that this is a different B, but the function certainly looks pretty similar. However, there is a lonely point in B that isn't targeted by this function. So that is what makes this right function not onto, because one of these elements is lonely. The other property is that a function is one-to-one if the only way for the outcomes of the function to be the same is if we started with the same inputs in the first place. Right? So this is a fancy way of saying that we never have two arrows targeting the same output element. Put another way, nothing in the target set is mentioned more than once. Using the same example from our onto property, we see that this same function is also one-to-one, and it's one-to-one for a different reason than it was onto. It's one-to-one because if we look at every point in B, there is only one arrow pointing at it. If somehow we had two things pointing at the same element, then if the function was one-to-one, it actually has to be the case that the two things are really the same arrow. They're coming from the same point. In other words, if f of a1 equals f of a2, then the only way that we can have that happen is if a1 equals a2 in the first place, which really is a fancy way of saying that every element in B is targeted at most once. Right. So here's a function that's not one-to-one, and it's not one-to-one because there is a point here, there's an element in B, for which two distinct elements in A, when we apply f, give us that point B. Right. Therefore, this function is not one-to-one. You may recall this idea of a vertical line test to tell if a function that maybe you've seen in calculus or algebra was actually a function. And what this does is it prevents situations like this from occurring. Right? If in calculus class you were asked what the integral of this function is, you would say that doesn't make any sense, this isn't a function. And the reasoning for it is that somewhere there is a vertical line that intersects the graph of the function in more than one place. So this is a property that we still want to have in our functions. We still want them to pass this vertical line test. But the reason I'm bringing it up now is because when talking about functions being one-to-one, there's also an idea of a horizontal line test to tell if the codomain has any points that are hit more than once. Going back to our first example, f of x equals x squared, defined from the reals to the reals, this function is not one-to-one because it fails the horizontal line test. We can find some horizontal line that intersects our function in more than one place. Let's say this function intersects, if this is 2 and this is -2, at 4. So the function f of x equals x squared has the property that f of 2 and f of -2 equal the same answer. Therefore, this is not one-to-one. Similarly, our discrete function in example 2 also is not one-to-one because it also fails the horizontal line test. There are multiple elements in our original domain that get mapped to the same entry, the same element in our codomain. We have multiple arrows pointing at the same answer, therefore this is not one-to-one. It's worth noting that this is also not onto because green doesn't have any arrows pointing at it. There's no element in our domain that results in green. I should also mention that this onto property goes by another name. It's often called being surjective, and we won't really use this term in this class. We'll try to stick to onto, but just so you know, for other classes, other textbooks, what have you, these two terms are interchangeable. Onto and surjective are synonyms. Similarly, one-to-one is also known as being injective. And again, these two things are synonyms, but we'll typically be sticking to one-to-one, but feel free to use the term injective instead. One last thing I want to emphasize is that this one-to-oneness and onto-ness are completely independent properties. They'll often go hand in hand with nice functions, but it's certainly possible to have any combination of onto or one-to-one functions, as we'll work on Friday. So here are a few examples of functions, again drawn in this sort of pictorial way, where we have a function that is both one-to-one and onto, a function that is onto but not one-to-one, etc. All right. These are repeats from the examples I've already used, and this bottom right is a new example that is neither onto nor one-to-one. It's not onto because we're missing a point. It's not onto because there's an element in the codomain that is not the result of the function. And it's not one-to-one because there's an element in the codomain that's the result of the function coming from different elements in the domain.